If you have clicked on this video, then you're either a maths lover or you've got an exam soon, or maybe both. But either way, welcome to Auzi's Young Learning Emporium. In today's video, I'm going to be going over a very simple explanation of the proof of why root 2 is irrational. So let's get into it. Now, before we start, we need to know these three things: the definition of rational numbers, what are coprime numbers, and a theorem which is going to come in very handy. So let's begin by looking at 1. The definition of rational numbers. So let's take a random rational number, r. Now this can be expressed in the form of p over q, where p and q are integers and q isn't equal to 0. This is by definition a irrational number. Now you may have heard this or you may not have, but this is basically what rational numbers are. But something we kind of miss sometimes is that p by q is always a simplified fraction. Basically, what this means is that a fraction like 3 over 6 is not simplified because we can find common factors of 3 and 6 and cut it out to simplify the fraction into 1 over 2. So that's basically what a simplified fraction means. So this also means that P and Q are coprimes. So now let's look at what coprime numbers really are. Coprime numbers are numbers which only have 1 as their highest common factor. So basically, if we take two numbers like 2 and 3, the only factor they have is 1 in common. Because the factors of 2 is 1 and 2. Basically, factors are numbers which fully divide another number. So, factors of 2 are 1 and 2. Factors of 3 is 1 and 3. So, basically, 1 is the only common factor, and thus 2 and 3 are coprimes. Lastly, let's look at the theorem, which states that if c square is divisible by p, which is a random prime number, then c is also divisible by p. C over here is a random integers, by the way. Before we move on, let's look at what prime numbers are. Prime numbers are numbers which only have two factors. For example, 2. 2 only has 1 and 2 as its factors. So basically, 2, 3, 5, 7 all are prime numbers because they've got two factors, 1 and themselves. Now, what this theorem really means is that in the prime factorization of c, we're going to have a to the power of x times b to the power of y and so on. And for the prime factorization of c squared, we're just going to have a to the power of 2x times b to the power of 2y. Why? Because when we multiply, basically, when we square c, we're going to be multiplying its prime factorization by itself. So this means that the exponents of these numbers, like a, b, and c, are going to add up. By the way, over here, a, b, and c are prime numbers. So what this really means is that in c square's prime factorization, there are no new prime numbers, and thus, if a or another prime number like p divides c, it must divide c square, and vice versa. Now, let's finally look at the proof. We're going to be using a method called proof by contradiction. So first, we assume that root 2 is rational. So the whole point of our proof is to prove our assumption wrong. Let's begin. So first, we can express root 2 in the form of p by q, where p and q belong to integers. By the way, that sign with the little inverted reversed e, you can say, means that it is a part of z, which means integers, and q is not equal to 0, and p and q are coprimes. This is what, by definition, rational numbers are, right? Since we can manipulate this as much as we want, let's now square both sides. So this means that 2, which is the square of root 2, is equal to p square over q square. This also means that 2q square, if we bring the q square up to 2, is equal to p square, or p square is equal to 2q square. Now this means that p square, and thus p, is divisible by 2 by the theorem we learnt. Now, next step, we can say that p is equal to 2 times c. C is some random whole number, right? Because obviously 2 divides p. So that means that 2 times a number is equal to p. Now, if we plug in this value into our equation from number 3, this means that 2c squared is equal to 2q squared, which means that 4c squared is equal to 2q squared. And that means that if we simplify and divide both sides by 2, 2c squared is equal to q squared, or q squared is equal to 2q squared, 2c squared, sorry. Again, from our theorem, this means that q squared, and thus q, is divisible by 2. But this is impossible, since p and q cannot have another factor other than 1. As we saw before, p also is divisible by 2, and so is q. So that means that they're not coprimes, and thus, therefore, our assumption must have been wrong. And so, root 2 is irrational. Here I've just written out the whole proof altogether so that you can have a look at it. Now, if you did not understand this proof too well, maybe you can try rewinding this video again or reading it again. I really hope it makes sense. But if you do have any questions, drop them in the comment. And that's all for this video. Thank you so much for watching. I really hope it all made sense, and I'll see you next time. Bye!